I am pleased to introduce Dr. Alina Glushkova, who is a researcher at Ecole in the AI Move group. So Alina's research is concerned with using AI to help humans learn new motor skills. And she works specifically with algorithms for visual perception of poses and movements and gestures. And her work has been applied toward the preservation of artisanal skills and the transfer of movements from experts to novice learners. So without further ado, please give a warm welcome to Alina Glushkova.
Good afternoon, everybody. Thank you for being here. I know that it's a tough time. It's 2 o'clock. No, 1 o'clock, but still, I will try to keep it short and as interesting as possible. So my name is Alina Glushkova. I am from the Center of Robotics, Mines Paris Tech. It's an engineering school. I guess that most of French people know it. We are one of the oldest engineering schools covering different fundamental disciplines of engineering, going from mathematics to computer science, innovation, and even science of management. Enterprises management. I'm working on human-centered AI to build algorithms to improve perception of machines, to better understand human behavior and more precisely human motion, human gestures, human postures, in order to build interactive systems that help the understanding, the interpretation of human motion, and also the learning of human motion. So, I would like to start by a very standard thing. What is AI? A definition of AI. I guess that you are all familiar with it. I put a pretty standard one. AI is a type of computer technology which is concerned with making machines work in an intelligent way, similar to the way that human mind works. So you see there is this idea of duplicating and imitating the way that our mind, after all, interprets situations in order to build an artificial way to do the same thing. So this AI can be applied to any field. You can collect a multitude of data from banking system, from hospitals, from insurance, from companies, and then trying to predict, trying to extract knowledge about these different fields. But what we do in my team is mostly focusing on human-centered AI. Can you try to identify the difference? What would be the principal difference between generic AI and human-centered AI? Any ideas? Please feel free, yeah?
Maybe you replicate the fonctionnement, the functions of the human brain, try to see how it works and implement it.
Could be. Would someone else give a try, yeah?
Maybe there is a much larger place for emotions because mostly AI, classic AI are like pure algorithm, and so maybe you can add the emotional aspects.
Could be, yeah.
Perhaps using everything that the human can do as inputs for the AI.
You get a point, yes, absolutely. Not taking inputs from banking system data, insurance system data, this very generic data, but taking as inputs data that come directly from human activities, human motions, human behavior, human feelings, human gestures, postures, whatever. So we try to give, to propose a definition in our team. Human-centered AI are concepts and methods of machine learning and pattern recognition, of course, because we are still talking about computer science, on signals recorded from the human body and that aim at a better understanding and interpretation of human activity. Because if we build algorithms that permit us to better understand automatically human activity, then you can imagine that we can build a multitude of interactive applications, make machines smarter, and make them able to react to the automatic recognition of humans' activity. So, for the last 10 years, we have built a methodology in my team, in our team, that I have tried to summarize here. It can be summarized on 6 steps. So first of all, how do we proceed? We use motion capture technologies, different types of mock-up technologies to collect human motion data in different contexts, depending on our project. Then, of course, this data, we need to analyze this We need to process it, we need to segment it, to annotate it, to cut it into smaller pieces. We need to clean it in order to get it ready to be used for machine learning. Then we also make feature extraction, because the data, from the raw data, we can extract an important amount of features. So we really need to understand which features are the most interesting to us depending on what we want to do. Then the first step, the most complex one, is to represent and model this data in order to define the patterns that are meaningful in terms of human motion and to train machine learning models in order to recognize these patterns. The fifth step is about the recognition, the early recognition and temporal alignment of the different human motion models that we define. And finally, if we are able to build algorithms that can recognize the human motion patterns, the human motion activities, then we can go until the final step, which is building interactive, collaborative interfaces that can be applied in different fields. And I'm going to give you some examples here. So the first step, motion capture. I guess you are all familiar with this, right? Just very brief overview. We mostly use in our team 3 categories of mockup. The wearables, IMU sensors, full body suit, gloves that permit us to gather rotations and accelerations of human body motion. We also use marker-based vision sensors like OptiTrack or Vicon. You have probably heard about them. They are of a high precision. They provide us data of good quality, but they are very expensive. Or we can also use the low-cost sensors, such as the basic cameras that you all have in your smartphones, or more specific cameras like the RGBD cameras, for example, that also permit you to gather the information about the depth access. So just to give you an example of mock-up work that we did in past, as I told you in the beginning, for the last 10 years, we work a lot with craftsmen, with traditional craft. Our first project was funded by the European Commission after the UNESCO Convention that states that it is very important to better preserve the traditional know-how that makes the European identity, different traditional crafts that tend to disappear for various reasons. And we have been funded to use multisensory technologies in order to go and get this data to digitize human motion. So in my thesis, I worked with potters from Greece and from France, the village of Valoris, where traditionally a lot of ceramists had their atelier. So here we use a half-body mock-up suit with inertial sensor with IMUs that permit to reconstruct the skeleton afterwards. We also use computer vision, but as you can imagine, when the hand is dealing with the agile, it is very difficult to extract the information. Where is the hand? Where is the agile? Where do they interact and how? We have also recently worked on traditional silk weaving, where we spent a lot of time in Germany in a small city of Krefeld that used to be the capital of silk weaving in Europe in the Middle Age. And we recorded this aged person working with a machine from the 18th century. And we were able to reconstruct in 3D his skeleton as well as his finger motions thanks to this technology. And unfortunately, because of COVID, this person is not with us anymore, so we could somehow numerize his motion data thanks to mockup. We did also similar work for another more original use case, an agricultural one. We traveled to Greece, to the island of Chios, in order to record the motion of agricultures who cultivate the tree of mastic of Chios. This tree gives actually a mastic product when it is correctly cut. But the island, the entire economy is facing important problems when they hire non-trained person to cut the tree and to collect the mastic, because the trees are damaged. So it is very important to go and first of all to preserve the correct way of performing by using different mock-up systems. And we also do the same for glass-blowing professions, where we travel to CERFAV, Centre Européen de Formation dans les Métiers du Verre in France, where we have recorded Jean-Pierre Mathéus performing La Carafe de Bon Temps. So the second step, remember, the first step is to get the data. The second step is to analyze and to process the data in order to extract the features. So what do we do here? If we work with multimodal data acquisition, we need to synchronize and to fuse the different signals that we get. Recently, we have started working also with audio signal. It was not the case before, so now we use also a microphone in order to collect the data from the noise, from the sound that is generated by the gesture. We need to synchronize, we need to fuse, we need to visualize it, we need to process it, to apply different signal processing techniques you might be familiar with, applying filters, low-pass filters, or in order to reduce the noise, because raw data is very noisy. And then we segment, we cut it into smaller pieces, depending on what we call the gesture vocabulary that we define together with the expert. Okay? We are guided by the expert, by the craftsman who tells us that in my process, I perform this gesture, but this gesture is constituted from other smaller gestural parts. Then, here are some examples of data processing, especially with the costume. You might know it, but the IMU's technology is pretty sensitive to magnetic disturbances. So if you record in a place with a lot of metallic devices, with cables or with computers, and this is often the case, your data might be very noisy. So we apply some data filtering to correct importance amplitude errors. Another example of feature extraction is here. You can see Jean-Pierre performing the motion. So here we have a recording with a video camera, okay, with an RGBD camera. And we apply a post-estimation skeleton over the body of the expert, and then from the X and Y and Z positions of his body, we extract the angles, okay, that in degrees, in Euler degrees. So we know if the expert does this or that motion, we can estimate the degrees between different joints. So after having prepared the data and extracted the most meaningful for us features, we use it in order to feed it into the AI, in order to build the AI models, to build the patterns. How do we do so? In general, in our team, we have two approaches. We use a lot stochastic modeling. For example, hidden Markov models. I don't know if you have heard about this method. Dynamic time warping that permits to align temporally different time series. This is what I did in my PhD. But since then, there is a new family of machine learning methods born. Which one? Don't see the slide. No. Deep learning, of course. Deep learning that has several advantages, but it still has the particularity of requiring a lot of data, okay? Big, important volume of data. And right now, we are trying to work with different methods in order to efficiently train the models with a reduced amount of data. Because as you can understand, this human-centered data is not downloadable from somewhere. You need to go, you need to take the sensors, you need to go and search for it, you need to record it, you need to create a protocol. And having this type of data in a correct format is a real challenge in our community. Then, after the training of the models, our goal is to being able to automatically recognize the gestures. So we train the computer, we train our software, we train our algorithm about the characteristics that are included in each motion. And then we asked to the algorithm, when the same gesture is performed, to be able to recognize which one is performed, okay? And if we are able to recognize it automatically, then we can develop, as I already mentioned you, a different kind of applications, interactive applications that might be used in various fields and disciplines. First of all, factory of the future, okay? You can imagine, I saw that you have a hackathon on le futur du travail. The use of mock-up, AI, for monitoring the activities of the operator for augmenting the capacities of the operator by using augmented reality, virtual reality technologies, by using mock-up, by using visual monitoring are topics that are very often mentioned by our industrial collaborators. For example, dealing with safety procedures or la gestion des oublis, developing interactive tools that would help the operators to better manage different very complex industrial manufacturing processes. Another application would be in cultural and creative industries. We had a PhD student in our lab who has developed an interactive interfaces to sonify human motion. Please don't fall asleep, please wake up. I will keep it short, I promise. So he used a gesture-based interaction to sonify human motion. And what he actually did in his thesis is to match and to map different motion parameters, such as velocities, accelerations, rotations, to sound parameters in order to control in real time sound synthesis. We can also have another type of applications which come from the vocational training, from the transmission of motor skills, of movement skills. And this is a requirement that we very often have from cultural and creative industries. For example, the French luxury good manufacturing industries. We recently won a 5-year project where we are going to work with 20 more partners, such as le Comité Colbert, la Maison Christophe, la Maison Van Cleef and Arpels, professional high schools, le lycée professionnel, on building together methods and tools in order to innovate, to stimulate, to motivate young generations to be trained on craft professions, okay? So vocational training is another field. And finally, some other sectors like autonomous vehicle, developing interactive interfaces for inside the cockpit to interact, for example, with your radio by using your finger motions, to control different devices in the cockpit by using gesture motions. We had some projects in the past. So I would like to show you a small video from one of the recent applications on human-robot collaboration. And then we will progressively get to the luxury industry. So in the human-robot collaboration, in the very beginning of the massive industrial production, the entire production was based on manual work, okay? On workers who use their body, use their gestures to fabricate things, to produce things. So, of course, this approach has advantages and disadvantages. From a human perspective point of view, some disadvantages that can be mentioned, among others, are the ergonomic risks. The fact that the labor was very physically demanding for the human, that errors are possible, but from the other side, human, through years of experience, develops a dexterity and becomes an expert in his manual work. Then, in the last decades, let's say, we passed to full automation, as you can see in this very short video, with advantages and disadvantages similarly. So we gained in terms of efficiency, precision, and speed of production, but we still had some loss of flexibility and even of cost, because these industrial robots are very, very expensive. And now the tendency is to search for a solution that would be in the middle, that would permit the complementarity between humans and machines, humans and robots, that would permit to go beyond a simple compresence towards a co-production, towards a partnership, a real collaboration. This is an example of the work that we did that goes towards this direction, where we have my colleague Gabriela, who is simulating the role of an operator, and she's collaborating in real time with a collaborative robot, and this robot interprets in real time what are the gestures, what are the postures of this operator, and adapts his behavior accordingly in real time without being pre-programmed. So the behavior of the robot depends on the input, as you mentioned, from the human directly. And this behavior of the human is interpreted by machine learning techniques automatically. So somehow, Gabriela wears an egocentric camera on her head, and somehow this camera becomes the eyes of the robot, you see? And the robot interprets what are the objects that Gabriela is dealing with and how does she places them on the TV assembly. This is a scenario about assembling a TV screen. And the robot is able to adapt its behavior based on the rhythm of the production. If Gabriela is moving fast, if she finished the process fast, then the robot will bring the next piece depending on her cadence. Then we also have a spatial adaptation. Gabriela is a standard-sized lady, but here we have Dimitris, who is a taller guy. So the robot, depending on their anthropomorphics, on the fact that if they are right-handed or left-handed, the robot adapts in real time its behavior. So this is what permits us to say that we contribute to the spatio-temporal adaptation of the robot towards the behavior of the human. Mobile robot, I think that I will pass this one. We also did some works on human motion ergonomy analysis, okay? All this data that we collect, it is an important asset. It constitutes an important volume of signal that can be automatically interpreted and that can tell us things that are not easily visible by human eyes. So we have done some works in the framework of a past research, H2020 research project that was called Collaborate, in collaboration with a factory in Turkey, in order to collect the data of the workers, analyze it, and apply actually an automatic analysis of the ergonomy of professional gestures above this paletting process. So the advantage of this approach is that it permits to automatically and pretty accurately identify the factors for ergonomic risks based, of course, on existing standard protocols in factories in the industrial world. So we also have developed an application that permits, by using color coding, to notify the ergonomist in a factory what are the human body parts that might be overloaded when performing a gesture, so that the ergonomist or the director of production process can redesign the process or can add a robot in the loop, so that the most difficult, the most hard tasks to be given to the robot and the most valuable, interesting, and dexterous task to be given to the human, okay? A final example is inspired from the cultural and creative industries, from the work that we did with the glass blowers. So one of the works that we did was to develop for le Musée du CNAM, le Centre National des Arts et Métiers, to develop an interactive installation that would permit to the visitor of the museum to physically experiment the postures and 3 basic gestures of a glass blower while receiving a visual and auditory feedback in real time. So we had to respect different constraints for this, for developing this experience, but still we also developed an evaluation mechanism that would take the data from a camera that tracks the skeleton of the visitor. Maybe if I show you the video, it will somehow help you to visualize what happened here. So at the Musée du CNAM, they have created an exhibition around les métiers du verre in order to valorize La Carafe de Bontemps, which is a chef-d'œuvre created by a high-level expert in the 19th century. And unfortunately, there were no archives at all about how this object was created. So we collaborated with Jean-Pierre, who did a process similar to inverse kinematics, let's say. He had He gave different trials in order to understand how the object was performed. And as I already mentioned you, we recorded his motion. So inspired from this process, we have developed an installation where the museum visitor was tracked by the RealSense camera, which is an RGBD sensor. And the visitor was invited to take a seat on a real glassblower bench to manipulate la canne, the pipe, and to imitate 3 basic gestures of the glassblower that the visitor could visualize over the screen. At the same time, the data that we collected from the camera was used in order to estimate the different pose, the different position of body joints in space. And then depending on the values of these body joints and on the result of a comparison with the data of the expert, we activated a feedback, a visual feedback. Maybe I can just replay this video for you. A visual feedback in form of circles that would guide the motion of the wrist. And we would change the color if the deviation was too important from a deviation that we defined as acceptable with our modeling process. Then we would change the color and we would transform it into red. So in order to remain inside the acceptable bounds, let's say, the visitor had to experiment with his body wrist positions in order to find the correct position. And we actually conducted an experiment, a similar one in the lab, in order to test different hypotheses concerning what type of feedback seemed to guide the best the learner when you want to find the correct posture and the correct position of the wrist. Is it the visual one? Is it the auditory one? Is it the multimodal one? And depending on different configurations and on different user profiles, we actually concluded to different conclusions. So the biggest conclusion is that this field is still to explore, and the discipline of generating augmented feedback by using machine learning is a relatively recent discipline. So there is still a lot of work to do. My conclusions from this late, let's say 10 years experiments, is that our goal, this is something that I repeat very often, in our team, our goal is absolutely not to build algorithms that would replace humans. Our goal is to build methods and tools that would permit to reach the complementarity between machines, robots, interactive interfaces, and humans, that would augment human capacities, that would take the physically difficult task and give it to the robot, but that would keep the dexterous, very demanding task and still keep it to the human, okay? As far as the learning process is concerned, all these augmented feedback interfaces, they are not developed in order to replace the master, because this is not possible when you're trying to acquire very fine motor skills on pottery, on glass blowing, on, I don't know, ceramic making, on painting or whatever. Because the in-person transmission is crucial, and this is how the learning by doing process is activated through the in-person transmission. However, when you are training yourself alone in your atelier or at home, you still have this passive position of not receiving any evaluation, not receiving any comments, no notification, no real-time feedback. So in these situations, for self-training, this augmented feedback interfaces and mechanisms, they can bring very interesting value, because they can put you from a passive learning position to an active learning position where you're going to receive a feedback and you will be expected to modify your motor behavior until you find the correct motor configuration, let's say. And in order to build all these interfaces and to go until collaboration, what is important is to build algorithms that permit to improve the perceptions of the machine, okay? Because if we have a machine that cannot understand what motion do you perform and how do you perform it, then we cannot really talk about a comparison, about activating feedback. So the very first step is to build and to improve perception algorithms. Finally, from a more philosophical perspective point of view, what we are trying to do is to adopt a human-centered approach and not a technology-driven approach, saying that, oh, okay, there is a new sensor of the market, let's try and let's just add it to our pipeline. Or especially in robotics, this is very often what happens. There are plenty of accessories that are integrated in the market regularly, and depending on the accessories, we will see what the robot can do. But what we propose in our approach is to have a different perspective of first analyze what is the need of the human, what is the need of the operator. Does he need to be relieved from certain tasks? Which are these tasks? How can we analyze his motions, his postures, in order to understand which task can be given to the robot? And I think that the key point to remember is that our goal is the complementarity between human and machines, and not at all the replacement of human activities and human skills by machines. Okay, and I think that I finished.
Thank you very much for this really interesting talk. Do we have any questions from the audience? Yes. We can pass the microphone. Yeah. Say your name first and then your question.
So my name is Guillaume. And my question is, I see that you are recording every movement, every noise, but are you going to record the smell for maybe the kitchen skills in the next step?
The smell. That's interesting because we had this discussion with Xiao this morning talking about different modalities that could be interesting. So far, we didn't work with smell. And even motion. Motion is a very rich set of signals. What we did so far is focusing on mostly kinematics. And inside the biomechanics, you can also find the family of kinetics. Kinetics is about forces that generate the motion. But so far, we focus mostly on kinematics, which is a group of ways that permit to describe the motion by using trajectories, rotations, accelerations. So you see, even what we do now is pretty restricted. It's limited. And the next step for us would be first to go towards kinetics, to also look on forces.
I had a question about trying to combine robots and human. The slide you showed, you said that the automation has increased the cost, but when you use human, it lowers the cost. But if you do both, doesn't it just increase a lot of cost because you have to pay the human and also to build a robot? So how's about the cost in the semi-automation?
That's a good point. By using both, you're expected to have synergies. So you're expected to gain cost because you will keep the advantages of a robotic production, precision, accuracy, 7 production. But at the same time, you will avoid you will still keep the flexibility of human hand, human dexterity, and you will also gain a lot in term of well-being. Because, for example, the TMS, les troubles musculo-squelettiques, is a real issue in industry, and also in the cultural and creative industries, dans les manufactures des produits de luxe. TMS is an issue, and one of the potential solutions would be to give the most difficult task, the most repetitive ones, to robots, and to keep the difficult from a motor point of view task for the human, where the human can fully deploy his dexterity and his creativity.
It seems like on several occasions you're talking about analyzing different features to determine, for instance, how correctly the gestures are being operated. And I find it very curious that you're operating in a geometrical space for these features, because it's very abstract from the human body. And so my question is, Have you ever considered using different features for evaluating movement quality or reproducibility?
Yes. The features we use depends a lot on the sensor that we use to collect the data. So if we use the IMUs that will permit us to get the rotation of a joint, then we will work with the derivative of a rotation, like the Euler angles, like the accelerations, like the velocities. We could even use quaternions, but it's a much more complex thing, especially in terms of interpretation. When we use vision, there are two possible approaches. Either we apply pose estimation and skeletization over the image that we get. And in these cases, we will focus on the positions of the joint in space, in 2D or in 3D. Because when I move, when I make a simple movement, my wrist is displacing from a point A to a point B. So this displacement can be represented in terms of distance, for example, from point A to a point B on 3 different axes. And the other approach when using images is to deploy the end-to-end techniques with deep learning, with the new possibilities and the new perspective of deep learning. The end-to-end has no feature extraction at all. We use just the image, the pixel colors, in order to train the models to understand what does the human does. So there are different families, there are different approaches, but it's true that the quality of motion is a notion that goes much beyond a feature. A feature is a pretty restrictive thing. After all, it remains a signal, okay? It's a time series, it's a bunch of numbers. So the extraction of the knowledge, how to get the quality from the data, from the feature, is a real question. And there are different techniques, the most famous one are the descriptive ones, like the Laba notation, if you have heard about it, which is a descriptive approach of trying to represent the quality of emotion by using different signals, like creating la partition du mouvement. So, but it's a different philosophy. From an engineering point of view, what we do is to work a lot with features, analyzing them, and trying to extract the knowledge from the signal.
Okay, can we talk about the TV assembly problem?
Yes.
I find it, I'm very curious, how do you determine like the progress of the task? Do you use a set of discrete features or key points that you detect? Or do you have some kind of continuous detection of the task advancement? And do you have support for instance, coming very close to finishing and then breaking the device and having to start from zero? Do you accept like reversing the progress or not?
Yeah, these are very good questions. I think you must have a nice engineering background, right? How do we do? The algorithm that we use takes 2 parallel inputs. We have the input from the end-to-end recognition here. You see, we have only the image from the egocentric camera. This is what I mentioned you. The eyes of the robot become the eyes the eyes of the operator become the eyes of the robot. And here in the blue box, you can have the real-time result of the probability of a recognition of what the person does. So actually the algorithm recognizes and tell you the operator is doing this or that. So based on this, the robot receives commands. It activates different commands. And depending on the speed of motion, there is a ratio that controls the speed of the robot and the reaction time of the robot to the gesture of the person. And what was the second part of your question?
Let's say you're 99% done assembling the PCB, and then all of a sudden you move the screws. Do you handle reversing progress or only forward progress?
No, we don't handle any reversing progress. It's a pretty straightforward approach where we follow the gesture. But what is interesting, indeed, in this scenario is to generate some non-expected classes, let's say, for which the algorithm hasn't been taught, okay, to generate some non-normal situations and to program also different reactions of the robot to these non-normal situations, like, for example, to do nothing, because something might have happened in the industry, in the factory, in the entire process. But in this work, we didn't add this type of non-straightforward scenarios.
Thank you very much.
Thank you very much for this amazing talk. I was curious to know more about why did you choose those data sets?
The use cases, you mean?
Not precisely. So one may think that the jobs, like the skills that someone is learning from glass work or pottery or something else concerns a very limited number of people. You know, there are not that many people working with that. So one may wonder why did you choose exactly those situations or those jobs actually to learn more about like motion capture or to develop your algorithms instead of using something that people do in their daily lives that is more like common to encounter as a situation.
First of all, the first project, the AI Treasures one, when I did my work on pottery, when I did my PhD, was funded by the European Commission of Research after the publication, let's say, of the UNESCO convention. So UNESCO, what they say that European heritage is not only material, it's also immaterial, it's also intangible, and it needs to be better preserved than what is done today, and it needs to be better transmitted because it is under threat, under disappearance threat, because of globalization, manufactural processes. And then there is a second part of something that we discussed also today with Xiao. It is the fact that the cultural and creative industry, and more precisely the luxury good manufacturers, they are getting ready today to face a not very positive socio-demographical phenomenon where their most experienced operators will be retired, massively retired, because they all belong to the same generation. And the problem is that they don't have enough young operators trained and operational in order to respond to the needs, to the development of the market. So they need to preserve first, better preserve the know-how that is going to get out from the factory because of the retirement. And better preserves means going beyond the video, because what is very broadly used is audiovisual signal, okay? And which is fine. Taking a camera and going and recording is already fine, and making a nice tutorial. But with mock-up, we can also try to touch a bit the biomechanics. We can get the signal that is rich of data. We can represent the motion in 3D. We can have access to the trajectories, the rotations, the accelerations, all this type of signal that I mentioned that can, if presented correctly, if analyzed correctly, that can be very valuable for the company. And then there is also a part on training. Beyond preservation, we also need to invent novel methods and tools in order to boost and to attract young generation to this craft, hand-based, to these manual professions, which are not that attractive in the eyes of young people today. So these are mostly the reasons.
Thank you very much.
Any more questions?
Yes.
Yeah, just
It doesn't work, but you have to talk. It's not the.
hello?
Yeah, but the feedback will do.
Okay. Just maybe it's a question, I don't know. Just you never talk about ergonomy, but it looks like to me you do that in fact.
Yes,
but
yes.
with robotic and AI, why you don't never use this word? There are already explanation for that?
No, it's just that, ergonomic risk, human motion ergonomy analysis and monitoring. Yeah, so these are one of is one of the applications that we do with the algorithms and the technologies that we use to extract knowledge about an automatic identification of factors that might make a motion dangerous, and in order to redesign some production processes in industrial applications.
Okay. Do you have a last question?
Yes, thank you for the presentation. Very great talk. We got a question from the online audience.
Okay.
The question is, what are your thoughts on the methods such as dynamic Gaussian splatting in combination to AR? The scenes could be wrapped to match the user's body and then superposed.
Okay. So, what are your thoughts on methods such as dynamic Gaussian splatting, real-time successor of nerves, in combination to AR? The scene could be wrapped to match the user's body and then superposed. I'm actually looking for a postdoc to work on nerves right now. So if you guys have a PhD, don't hesitate to apply. So yes, first of all, what nerves are? It's deep learning-based methods that permit to reconstruct a scene, reconstruct an image, a scene in 3D dynamically when this scene is changing. So indeed, of course, this is a very interesting idea. Because when, for example, you are creating a pottery, or if you are creating a glass object, the know-how is not only about motion and kinematics and kinetic. The know-how is also about how does your material react to what you do, right? Because after all, you want to create an object. You want to create it correctly without harming yourself, but still you want to reach a goal. And your goal is to have a nice carafe de bon temps, or to have a nice ceramic vase. So nerves actually is a method that would permit us to better analyze, model, and interpret the different interactions between human body, finger motion, for example, and the impact on the material. So yeah, there are some interesting perspectives. And yeah, we are currently looking for a postdoc to work on these topics.
We got the second question.
Second question, yes. Could you derive a model from the skeleton to compute the constraints, tensions applied to the joints? This would enable optimization of the superposed model to guide in effort optimization. Absolutely. We can use pose estimation and skeletization to extract information about the body posture and about the tension of different parts of the body. Like, for example, again, we talked about this with Xiao. For example, in general, in different type of motor skills, when you are stressed, your first natural body reaction is to tend your muscles, to tense your body, okay? So this is an information that is possible to detect automatically and pretty easily by using pose estimation and skeletization. But more precisely, if you want to work with muscles, you need to use different type of sensors like the EMGs, for example, which is a pretty complex sensor, very noisy, giving a data of, de qualité discutable, it depends. The experience that we had in the lab with EMG is not satisfying. Okay, that's all? Yes. Okay, last. Yeah, oops, sorry.
My last question would be, given the specificity of those skills that you need and the transmission that is not, as you said, not at all easy to transmit just by video or explanation or even imitation. So like even the kinesthetic, like the kinematic transmission is not covering fully the skill. There's some part of it that is like
Part of it, yes.
Do you tackle that part in your doing comparisons maybe?
Yes, that's a good point. This is what we are trying to do through a method that we developed for human motion modeling, which is a hybrid biomechanic and stochastic approach of mathematical representation of human motion model. So actually we are trying to reveal different assumptions, different relationships that might exist between different body joints when performing professional gestures that are not visible with our eyes. For example, we are trying to measure the synergies between the hands when performing, how strong it is by using different coefficients. We are trying to measure what we call the mediation. It means the transitions, how strong are the transitions between the different neighbor body joints when performing the motion. We also try to look on the relationship on body joints in time in comparison to past. How does the motion evolve? So we are trying to do so by using mathematical modeling, but again, of course, we need to take into consideration that human motion it's a stochastic process. Even if you are an expert potter and I am an expert potter and we are performing the same object, we will not do it in the same way. We have different techniques, different styles, and this is what I saw when I did my PhD and I worked with an expert potter in Greece and an expert potter in France and Valoris. After all, they produced the object with the same specifications, the same size, but in a completely different way. So we can apply mathematics to better understand human motion, but there are still a lot of things unexplorable.
And I think that's a wonderful conclusion to this talk. So thank you very much.
Thank you.